Well, hello everyone. It's Dr. Green. Wanted to just go over the lecture for this week. Let me go ahead and share my screen here, and we'll get started. Okay. So this week we're going to be talking about variables and validity. Okay. So really the conversation about variables and validity really starts when we talk about instrumentation. Okay. This really gets important when we are trying to make a decision or trying to describe how it is that someone collects their data. Oftentimes, people will utilize a specific protocol or a specific device within a study to collect data. So that data uh, often is called instrumentation. And when that data is utilized inside of a research manuscript, the author will often write a section um, describing the methodology of how that instrumentation was used. And so, instrumentation is a very, very important part, obviously, of any research manuscript and also of any research project, because there are a lot of considerations that go into not only what instrumentation to use, but how that instrumentation might actually affect the outcome of a study, right? So we need to first talk about validity. The reason why it's important to look at the validity of an instrument is because validity tells us that an instrument is measuring what it is intended to measure. And validity is not necessarily a perfect definition, it's more of a range. So if we have this illustration of a target here on the screen, you can see that in a perfect world, uh, our instrument would be able to essentially, you know, hit the bullseye every time. We would throw, a dart or an arrow perhaps or a lawn dart and be able to hit the bullseye, right? That is called being perfectly valid. So the instrument would be perfectly valid if it intended what it if it measured what it intended to measure without any error, right? But often, obviously, we live in a very imperfect world, and as we talked about last time, the struggle between internal and external validity. Oftentimes, the higher internal validity that a study has, the lower external validity that a study will have. So those things often work against each other in the real world. However, sometimes with instruments, particularly those that are often used, they do a decent job of measuring what they're supposed to measure with some error and maybe applicability to the external environment. So obviously, that instrument then would measure, maybe mostly what it's supposed to measure, but not to the extent that it should in a perfectly controlled environment. So, and then obviously an instrument that is less valid only somewhat measures what it's supposed to. So validity itself is obviously a range and not an exact definition. So there are different types of validity that can be, often described or utilized, right? And so one of them is face validity. And an example of that is, is an instrument valid based on the opinion of experts in the field? So, for example, an example that is used is, let's say that you're creating a simulator for pilots, right? But in creating that simulator, uh, you have placed shapes like triangles and circles and those types of things on the screen, um, as opposed to an actual picture of an airplane. So a pilot, a well-trained pilot who's considered an expert in his field, may look at that instrumentation and tell you that it has very limited face validity because it's not applicable to experts in the field. And because this instrument that you have developed does not actually contain a true simulation um, of a commercial aircraft, then it will not appropriately measure a pilot's ability to operate that aircraft. So that's an example of face validity. So criterion validity. So for example, criterion validity. So how well do variables uh, do variables validate or measure uh, the validation of a criteria? For example, if we were looking at, let's say, levels of cholesterol, levels of plaque on the artery walls of a patient, and we wanted to attempt to rank that based on mild disease, moderate disease, or severe disease, certain levels of arterial narrowing would that be broken down into categories, then being mild, moderate, or severe disease. So, based on the opinion of experts in the field, um, those levels of disease, mild, moderate, or severe um, atherosclerosis, are described and defined based on that level of narrowing. So, variable matching up to a criteria based on the opinion of experts. And then lastly, one that's very important that you'll often see in the literature is construct validity. So this is really interesting. So we see this a lot, particularly in applied sciences like kinesiology, psychology, and even in healthcare. We've begun to see the presentation of constructs to describe the outcomes of studies, right? We're attempting to measure constructs. For example, intelligence is one that's often used in psychology, right? We'll use constructs like, uh, you know, wellness is another one that you might see. How does someone describe wellness? And really that there's really not a definition for that, but it really falls into a construct with many different variables. And so construct validity looks at how well a variable measures up against a broad construct that is known to have specific parts or variables. Okay, but what about reliability? Okay, so let's say in our last example with the bullseye, we had a highly valid instrument. We were hitting the bullseye every time, but you know, maybe once we hit the bullseye, once we hit the outer ring, once we hit the middle. So, you know, ultimately we can see that in order for something to be reliable, that level of validity or that outcome should be reproducible over and over again. So we can see our little stick figure here in the slide saying, well, you hit the bullseye, but maybe you got lucky. Can you do it again and again and again? So very often, just like with our measurements, we expect our scientific literature to have a high level of reliability as well. And we accomplish that through the reproduction of studies, right, over and over again to establish a reproducible principle within the scientific method. Obviously, so here with reliability, we are attempting to produce a consistent measurement that is valid and do it repeatedly. Okay, what are the effects though of of validity and on of variables rather on validity and reliability, right? So, for example, that variable, okay, that we are manipulating is called our independent variable, the thing that we are changing or manipulating in our experimental study. Okay, so for example, what is one example of internal validity? Okay, and that is, in our example, a test measuring work performance, maybe number of tasks complete per week. Okay, however, and we can see here that that could be a pretty reasonable or a pretty valid variable for measuring productivity, right? For determining who gets a raise at work and who doesn't, right? However, there could be confounding factors that would impact the reliability. Okay, for example, we know that a test that measures work performance, number of tasks completed per week, right? Generally speaking, will have a high level of validity and also a generally high, a moderately high level of reliability, depending on the week. But here's the problem. What if all of the same employees are taking the exact same evaluation every year, and some of those have been working for that company for 20 years, whereas others have been working there for maybe only a year or two, right? Problems may actually pop up because those employees that have been there for 20 years and are more experienced are consistently meeting and exceeding uh, those task completions and scoring high on work productivity. Therefore, those people that have been with the company for only a year or two are not as eligible for raises as their more experienced counterparts, for that very reason, because there is a confounding factor of number of years present at the company. So there are different types of variables, right? So a nominal variable. Okay, for example, if we were looking at different types of cats, wild cats, for example, tigers, lions, ligers, if you're into Napoleon Dynamite, um, those are all different types of nominal variables or categories that you may come across. Okay, ordinate variables are variables that are ranked or ordered in a category, such as first, second, or third, right? Um, so interval variables are variables in which there is a known quantity between two measures of that variable. For example, height and weight. We know that per each foot, right, there are 12 inches. Per each inch, there are 2.54 centimeters, right? Um, and that measure of centimeter, right, is always constant. The measure of a pound or a kilogram is always a kilogram. And there are units that describe and delineate uh, 1 kilogram from 2 kilograms. Okay. A ratio obviously is a variable with absolute zero. So an example of this is temperature, right? So 0 degrees Kelvin, often in physics, is described as the absence of heat, a complete absence of heat. And so there is a real measurable zero with a ratio variable. Okay, so as we mentioned, right, the independent variable is that which the researcher is manipulating, whereas the dependent variable is the behavior or characteristic that is affected by the independent variable. So the dependent variable is our outcome. That is what we are hoping to measure based on the introduction of the independent variable and how we manipulate it into the experiment, right? So the independent variable we manipulate or change, and the dependent variable um, is our outcome that is affected by that change. So an example of this, once again, my favorite movie. Um, I don't know if one of my favorite movies. I don't know if any of you have seen this scene. This is where they're in a restaurant and eat a pepper, and in this scene, Harry passes Lloyd the ketchup and mustard because his tongue is on fire, right? And so in this case, the independent variable, the thing being manipulated, is the ketchup and mustard. It's the condiments, right? So, and then Lloyd poses a question, a research question, and he says, Harry, are you telling me that condiments lower perceived temperature after eating spicy peppers? So we can see that the condiments, okay, are the independent variable, and the outcome or the dependent variable that we are hoping to measure, right, is perceived temperature. All right, so condiments are being manipulated to test their effect on perceived temperature. All right, so let's talk about these independent variables here really quickly. So it's really important that we ensure that these variables, okay, that they are also valid, that they are measuring what they are purported to measure. So these variables themselves, it is preferable that these variables are backed up in the scientific literature as being valid, and that they are valid when we have seen that these have been used classically in the literature, right, in the scientific literature, um, when solving similar problems. Okay, now the variables also, in order to ensure that we are maintaining a high level of internal validity, the variables have to be applied to the experiment in a systematic and consistent manner. So, for example, every participant in the study should be given the exact same amount of ketchup and mustard at the exact same time in the exact same way. Okay, so an example of that is that each participant should receive a 1 ounce cup of mustard and a 1 ounce cup of ketchup at 11:30 in the morning, right? And that should be ingested orally um, at 11:30 a.m. on the dot. So the other thing too is that there are times when a participant might have a bias, right, uh, to a specific to the use of a variable, right? So these variables have to be applied in a manner in order to neutralize the effect of bias. Okay, we call that blinding. Okay, in research, oftentimes, if we want to have a high level of internal validity, often we will blind subjects to the variable that they are receiving. So how could that work in this case? So our hypothesis is that ketchup and mustard, ketchup and mustard lower perceived temperature after eating spicy peppers. Okay. However, however, okay, we we know that there are some people in this study that may have an opinion that ketchup and mustard already does not lower the temperature, affecting their ability, right, potentially to participate in the experiment. So what do? We're going to need to introduce a third condiment into the mix that will serve as um, essentially a placebo and or a variable that may neutralize the effect of bias. We're going to use relish in this case. So for example, what we will do is we will blindfold our participants. Okay, we will provide some of them um, with ketchup and mustard, and some of them in a randomized fashion will receive relish. And we'll compare the difference between those groups. Does ketchup and mustard lower perceived temperature, or does relish lower perceived temperature more than ketchup and mustard? And so we'll test that relationship to see which one of those produces the biggest measurable difference. So, and obviously another way that we could potentially blind our participants, um, is by, potentially numbing their tongues with maybe something that's cold. That's another thing that we might be able to do. However, we need to be really careful with procedures that would, you know, take away the ability of our participants to potentially feel or taste, right? So there could be some ethical concerns there, and we'll talk more about that this week too. Okay, external validity. So it's a big deal, right? Um, there are there are a lot of questions that we need to ask when setting up our research question in our study. We need to do a really good job, okay, of reviewing the literature to try and see that has this been studied before, and if so, how has perceived internal temperature been defined within the literature up to now? Okay, what is the working definition of perceived internal temperature? And how has that been defined? We can then take that definition from the literature and utilize that in our study to ensure that we are meeting the broadest criteria with our question for the broadest number of people so that our findings are the most generalizable to the environment. And the other thing is, how representative is our sample of the whole? So for example, let's imagine that we did this study in the Midwest. I've had coworkers that think ketchup is spicy. Okay, as opposed to maybe if we lived in Texas, where I'm from, we have people there that often eat hot peppers and salsa for breakfast, with breakfast, and don't seem to have a particular aversion to spice. So could it be that if we perform this experiment in the Midwest, could ketchup and mustard be effective in lowering perceived internal temperature? Maybe it would. But what if we did this in El Paso, Texas, where people chile and salsa nearly with every meal and don't seem to have as big of an aversion to spicy foods, right? Generally speaking, it very well could be that the results of our study may change based on the sample that we are testing. Right. So it's always important to ensure that the sample that we are testing is representative of the broadest swath of the population possible. And then we have to ask the question, how much of our results based on these other two criteria can be applied to the population as a whole? And often we'll address any shortfalls or pitfalls of our study in the limitations section of a paper in the discussion section. Okay. So we can see, obviously, right, that this whole process works together in order for an instrument, right, with variables that are being used to measure something, that instrument must be valid. It must measure what it says it's going to measure. that the measure itself must be reliable, meaning that the valid measurement must be reproducible again and again and again over time in order to be highly reliable. Okay, internal validity. We need to have a high degree of internal control um, in our study to ensure that there are no threats to the independent variable producing an effect on the outcome or the dependent variable, right? Obviously, we will have varying degrees of external validity, but the greater level of external validity we have, the better. Because if that is the case, right, our data then becomes more generalizable to the population at large and more reproducible. And that is exactly what we want. Okay, when we do this, okay, we have science working as a whole in our favor, and the scientific method is being utilized to its full potential. But what happens, okay, if we have confounding factors that threaten the validity? For example, we use an instrument that is found to be only minimally valid, and we produce measurements uh, from that variable that are highly unreliable, meaning that we are getting highly inconsistent measures, right? Highly inconsistent measurements of this variable over time. Okay. Not only does that have an effect on our internal validity, right? Meaning that we cannot trust our experimental process, our methodology comes into question because of the threats to our validity and reliability and our internal validity. But because of that, our threat to our external validity is heightened because we did not produce a sound scientific experiment based on those threats to validity and based on our low validity, low reliability, and the threats to internal and external validity. Because of those reasons, the scientific community and other researchers will not want to reproduce our study as we designed it because of these problems. And so here are the references for this PowerPoint. I hope that this was useful and helpful for you. Uh, there will be a quiz posted for you that will open up this evening, and we'll look forward to talking with you guys again on Thursday. Bye-bye.